Okay, looking at question 1 on the practice exam, we've got our triangle, we've got an angle that's been given, we've got the opposite side to it, and we've got the hypotenuse here. So we've got H, we've got O. So because we've got O and H, that means we're looking at sine. So we can write down sine theta equals opposite over hypotenuse, always writing down the formula first. Substitute in known values. Sine of 43 degrees is equal to the opposite, which is x over 22, and that means we can rearrange, multiply both sides by 22, and we get x equals 22 sine 43 degrees, which is equal to 22 sine 43 is going to be 13.75. And our units are centimetres. So if we're not told explicitly how many decimal places to round to, just stick to 2 decimal places. We've got question 2 here. We've got a composite shape. Composite shape is comprised of a semicircle, and we've taken a trapezium out of it. So that means to find the area of the figure, we're going to be taking the area of the semicircle, so area of the semicircle, and taking away the area of the trapezium. So we need to write down that we're writing that that relationship, the relationship to find the total area. So the area of the semicircle is going to be 1/2 of pi r squared. So substituting in formulas now, and the area of our trapezium is going to be 1/2 a plus b multiplied by the height of the trapezium. The radius of our semicircle is given here as 0.7 metres. So this is going to be 0.7 metres squared minus 1/2 of a, which is one length here of the trapezium, 0.25. plus the other length here, which is all the way across the semicircle, 2 times 0.7, which is 1.4, and multiply that by the height of the trapezium, which here is 0.3 metres times 0.3 metres. If we substitute this into our calculator, 0.5 times pi times 0.7 squared minus 0.5 times 0.25 plus 1 plus 1.4, all multiplied by 0.3, we get 0.52 square metres. And that's the area of our figure below. Notice the things that we've included. We've got here a formula that shows a relationship for our composite shape. We've substituted in the relevant formulas for each part of the shape, and then made the calculation, or substituted in the values, made the calculation, and expressed it in square metres. 2 decimal places, just to because we haven't been told how many decimal places to give it to. Next, we're asked to calculate the surface area of this solid. We've got a cube, and on top of that we've got a cylinder. So if we have a look at the cube, we've got the total number of square faces for the cube is going to be 5. On the top, we don't have the whole face. We've only got parts of it that are actually exposed. So the surface area of our solid is going to be comprised of 5 times the area of square. Each of these ones here, we can call them probably best to call them A1. Yeah, so we've got 5 lots of that area there. We've got one circle on top here. We can label that A2 plus A2. We've got here also our wrapping around our cylinder, A3, that's another shape, plus A3. And then we've got our last area, which is on top, A4, on top of the cube and on the bottom of the cylinder. So we can call that A4 there. So now we can substitute in our values for each of those different areas. So 5 times side length squared, or L squared, whatever you like. A2 is 1 pi squared for the circle shape. For the A3, this is made up of a rectangle that wraps all the way around a cylinder. So this is going to be the circumference of our cylinder, C equals 2 pi r, and we've got the height of our cylinder here. So the actual area of that is going to be 2 pi r multiplied by h, and our value for A4 is going to be the area of a square minus the area of a circle. So the area of the square is going to be the side squared minus pi r squared for the area of our circle. So we can substitute in now. Our side length is 10 squared. The radius of our circle, the diameter all the way across is 10. So that means that's 10 meters there. So the diameter must be, the radius must be 5 squared plus 2 times pi times 5 times the height. The height there is 8 meters there, plus the side squared, which is going to be our 10 squared minus pi times 5 squared. And this will be the total surface area that we have of our shape. So 5 times 10 squared plus pi times 5 squared plus 2 times pi times 5 times 8 plus, and then we do our 10 squared minus pi times 5 squared, and we get 851.32 square meters for the surface area of that shape. So top tips for any time you're given finding the surface area, you just need to find out what shapes it's comprised of. So for our shape here, there were 5 of the squares plus the top circle plus the rectangle that wraps around the cylinder plus the area in between the cylinder and the cube that's showing there. Next question, looking at question 4, we're trying to find the unknown angle. So here, there are many different ways we can show this unknown angle. We're given every side length. So you can use sine, cos, or tan. But I'm just going to use tan. Tan of theta is opposite over adjacent. So that means if we substitute in our value, tan of alpha that we're trying to find is opposite. So the opposite side is 1.05. The adjacent side is 1 meter here, divided by 1. And so that means alpha is going to be equal to the inverse tan operator, 1.05 divided by 1, which is equal to inverse tan 1.05 divided by 1, I don't even need to do that, and I get 51.55 degrees, which makes sense. It should be very, very close because 1 and this number here are very, very close to 1. They're very close to the same. That must mean that these angles are very, very close to being the same. And in order for those two angles to be the same and this angle to be 90 degrees, that means they need to be around about 45 degrees. And this is very close to 45 degrees, only a few degrees off. Now we're looking at modelling and problem solving questions, so we need to make sure that we can use our problem solving to solve these and figure out what strategies we might need to use. So we've got a balloon on the end of a string being blown by the wind. When the balloon is 31.75 metres above the ground, the string makes an angle of 19 degrees to the vertical. Calculate the length of the string. So we've been given a diagram that shows this problem. Unfortunately, we don't have a triangle that we've got all the information for. So we've got the side lengths and the side length that we need to find. We've got an angle, but it's outside the triangle. 19 degrees to the vertical, though, means that this line here is parallel to this line here. Because they're parallel, we can use the Z rule to find that this is 19 degrees. Okay, so we can then say, all right, that angle is going to be 19 degrees. We've got the adjacent side and we've got the hypotenuse that we're trying to find. So that means we need to use the cosine relationship. Cos theta equals adjacent over hypotenuse. So cos of 19 degrees is equal to the adjacent side, 31.75 meters, divided by the hypotenuse, L. To rearrange this, we need to multiply both sides by L, and we get L cos 19 degrees is equal to 31.75. And that, if we divide both sides by cos of 19 degrees, we get 31.75 divided by cos 19 degrees, which is equal to 31.75 divided by cos of 19, and we get 33.22 meters. So we then need to make sure, because we've answered the question, we need to answer the question in words, so we can say, therefore, the length of the string is 33.22 meters. Next question, we've got our circular oval of radius 50 meters. So the radius is 50 meters. That means the distance from here to here is 50 meters. Is marked with spray paint to form a square pitch as shown. Determine the area of the school oval that is not part of the square pitch, rounding your answer to 2 decimal places. Well, this question seems pretty challenging. We need to work out the area that is not part of the square pitch, this area here. So we've got a composite shape problem, but we don't know the dimensions of our square. We know the dimensions of our circle, we've got its radius, but we don't know the dimensions of the square. We need to figure out how we could find that out. If we know that the radius is 50 meters, that means this length all the way along, if I'm looking all the way along here, is 100 meters. And this is these are the sides of our rectangle, of our square. Now I know that that is a right angled triangle right in the middle here. So because it's a square, square has right angles in its corners. So it's 100 meters on the hypotenuse of this square. We also know that this side length of the square, x, is the same here. So we can use Pythagoras to determine the dimensions of our square. So we can say x squared plus x squared equals 100. That means 2x squared equals 100. I can divide both sides by 2 and get x squared equals 50, and I can get x equals the square root of 50. So that means the side length of our square is 50, is square root of 50, which is approximately equal to 7.07. Now I'm going to keep that number in the calculator because it says to round the answer to 2 decimal places, and I want to make sure I round right at the very end. So in order to determine the area that's not part of the square pitch, that is going to be the area, the total area is going to be, or the area that we need to find is going to be the area of the circle minus the area of the square. So the area of the circle is going to be pi r squared, and the area of the square is going to be x squared, or the side length squared. So then we can substitute in the values that we now know. We know the radius is 50 squared, and we know that the side length is square root of 50. Here's the interesting thing. If I have the square root of 50 and I square that, so if I take the number that I've got in my calculator and I square that number, answer squared, I get 50 there. So that means that this is going to be equal to pi times 50 squared minus 50. I can put that into my calculator. Pi times 50 squared minus 50, and I'm going to get 780, we're asked to round to 2 decimal places, 7803.98 square metres. So then I can say, therefore, the area that is not part of the pitch is 7803.98 square metres. Next one, we've been asked to prove that AD is the same length and is congruent to BC. So if we can prove congruence with this shape, then we can prove that AD is equal to BC. So first step is to state things that are the same so that we can make them equivalent. So I can say angle ACB, which is this angle here, angle ACB is equal to angle BDA, which is this angle here, because that's given. So we give the reason, given. That's given to us. I can also say angle ABC is equal to angle ADB. So that is also given because those angles are this angle here and this angle here. They are equal. I also know that side AB is shared. So I've got angle, angle, side. So then I can have a statement of congruence. Therefore, triangle ABC, and it's very important that we get the order right. So ABC, A is the equivalent point to or vertex to B. So we need to start with B on the other triangle, and then we start by going up along the long side we go along the bottom because we go B, A, and then up to C, and then up to D. So, and then we give our reason here for this one as well. Angle, angle, side, because this is an angle, this is an angle, and this is a side that they share. So now, because we've got that these two triangles are congruent to each other, I need to make sure I use the congruent symbol and not equal symbol. AD is congruent to BC. That means they need to match up. So AD is here, AD, and BC matches it perfectly. So we can say then, therefore, AD is congruent to BC because those two triangles are congruent. So triangle ABC and triangle ADE are similar. Show that show that any triangle divided with a line parallel to any side will produce two similar triangles. So we need to do another proof here. So what we've got is this angle here is shared between them. So let's start with that. Angle EAD is equal to angle CAB. And we know that because it's shared. It's shared between them. We also know that this angle here is equal to this angle here. Why do we know that? Because of the F rule, corresponding angles rule. Okay, we can see there's our transversal here, transversal crossing our two parallel lines. So we can say angle AED is equal to angle ACB, and that we can use the F rule symbol here, F rule. We also know back on this other side that this angle here is going to be equal to this angle here. And the reason for that is also the F rule, because we've got our parallel lines here, we've got our transversal here. Those are corresponding angles. So that's angle ADE is equal to angle ABC via the F rule here. And then we can say, therefore, triangle ADE is similar to triangle ABC. We can also use, and then we can write the rule, angle, angle, angle. That's why, because we've got one angle here, one angle here, one angle here, so that means they all feed in to it being angle, angle, angle. We can also write, instead of the 3 lines that are vertical, we could write a single squiggly line instead if we wanted to there for showing that they're similar. So we can then say, therefore, any two triangles, or any triangle divided with a line parallel to any side will produce 2 similar triangles. Question 9, what we've got here, we've asked first A to prove that triangle ABC is similar to triangle BDC, which is similar to triangle ADB. So let's try and find and prove that triangle ABC is looking at B is equivalent to BDC. So A, that means A here matches to B. B matches to B on that other triangle. It'd probably be easier if I color coded them. So A matches to B here. B matches to D. And also C matches to C. So we've got our 2 triangles there. All right, one triangle, the first triangle is the big triangle here. ABC, and we've got our second triangle here, which is BDC. BDC here. So what we can do, we need to make sure that we look at angles here, because we do not have multiple sides that we can say are in proportion. We're only given one real side length for each triangle to prove them. So we need to use our angles and have a look at our angles. So let's look at angle ACB. So we can say angle ACB is equal to angle BCD. And the reason for that is because it is shared. Now, if we have a look at the angle here, CDB, angle CDB on this triangle, CDB is going to be equal to angle A. No, it's not. It's going to be equal to angle CBA. And the reason for that is because they're both marked as 90 degrees. The final angle must also be the same. The reason for this is, if we know 2 angles are the same, we know that there are 3 angles that in a triangle, and they add to 180 degrees. So if 2 of them are the same, then the last one must be the same as well. So we can put in here, okay, angle ABC is going to be equal to angle BDC, and we can put the reason there because a reason is that there's 180 degrees in a triangle. Now also, I didn't really put the reason here. This is given for the line above. We need to make sure we do that. So we can say, therefore, triangle ABC is similar to triangle BDC. And we've proved similarity there. Now, I'm not going to look at doing the other one as well, but you prove it in exactly the same way. Prove it in exactly the same way, because we're looking at ADB for our other triangle, right? Angle ADB, or triangle ADB. we know that this angle here is 90 degrees. It has to be. This angle here is 90 degrees. This angle here is shared. So that angle there is shared between ABC and BDC. So we've got two angles, and that means that this final angle here must match up with the last angle here. Okay, so we've proven then that the triangle ABC is similar. Triangle ABC is similar to ADB. Now we only need to prove twice. We don't need to prove. We only need to prove that this is similar to this one and that this is similar to this one, because by association, if those two are similar to the first one, that means these two are also similar to each other. Okay, so we only need to do 2 proofs. We don't need to do 3 proofs on this one. Let's look at the final question here. So the final part says determine the unknown lengths x, y and h. So x, y and h, we need to have a look at the similarity and look at the scale factors. So here, if I look at the hypotenuse of ABC, triangle ABC, that is 68. The hypotenuse of triangle BDC is 32. The hypotenuse of triangle, because it's here, this is the hypotenuse, it's opposite the right angle. The opposite one for ADB is 60. So this is where we get our scale factors from. So if we look at trying to find, determine, say, x. Let's look at x. So x is on the side of BDC here, triangle BDC, and it corresponds to the triangle 32 being on the same side length here as triangle ABC. So the scale ratio, scale factor between ABC and BDC is going to be, based off these ones here, it's going to be 68 divided by 32, and 68 divided by 32, I'm just going to double check so that I don't make a stupid error, is 2.125. So we know the side length that corresponds to x is equal to 32 in triangle ABC, because if I rotate the shape, x is going to be corresponding to 32. So we can say here that CD corresponds to, CD corresponds to BC. So that means that x is equal to if I look at the original divided by the enlarged one, so the original divided by enlarged, sorry, the other way around, enlarged divided by original is going to be equal to 2.125, the scale factor, and the enlarged one is going to be the 32 over x. So that means x is going to be equal to 32 divided by 2.125, and we get 15.05. Now we can work out what y is equal to. Y is going to be equal to 68 minus the 15.05, because y is AD, and AD plus CD is equal to 68. So we can, if we add them together, we get 68. So 68 minus that value is 52.94 units, and we're looking for h now as well. Now we can use a range of different values here, but we know that it's a right-angled triangle. So one way we could do it is we could use Pythagoras. So we could say, well, c squared equals a squared plus b squared. So c squared is 32 squared for that triangle, because that's the hypotenuse. A squared is x, so it's 15.05 squared plus h squared. So h squared is going to be equal to 32 squared minus 15.05 squared, which is equal to 32 squared, which is equal to 797.5, and then h, so I probably should have left enough room, is going to be equal to the square root of 797.5, which is equal to approximately 28.24 in our unit. So we've found x is equal to 15.05, our y is equal to 52.94, and our h is equal to 28.24. There are a number of different ways of solving this problem. You could have a look at that scale factor and scale all of the other sides if you wanted to in order to find y and h, but you only really need one of x or y before the other ones can fall into place using different methods. It's up to you which you feel more comfortable with or which is easiest. Definitely looking at x plus y equals 68 is going to be the most easy way to solve for either x or y once you've found the other one, because it's one very simple calculation. You don't have to worry about scale factors or using multi-step procedures and algorithms like Pythagoras.